So this is the second session on building and assessing model, and this time I will be talking about growth curve modeling. The example I will be using throughout this presentation is from the last in-class exercise, where we had alcohol use as the outcome variable in youth. These were adolescents, ages 14 to 16, and there were two level 2 predictors in the model. One is COA, which is if the adolescent is a child of an alcoholic. And the other one is peer, which is peer's use of alcohol. And so COA is a binary predictor, yes or no, and peer is a Likert scale predictor that has, I believe, 5 values. We talked about this briefly last week. And before you start building the model, you go and investigate the shape of your level 1 model of change. What do I mean by model of change? You're looking at your outcome and see how does, in this case, alcohol use change over time within people and across people in a descriptive way. And so when I talk about shape, is it linear? Is it curvilinear? What is going on there? Because that is something you need to know to model your data appropriately. Obviously, you will always want to use your theoretical framework to guide, but you also want to investigate your data so that you can make smart decisions. And then you also want to investigate possible level 2 predictors. There are ways of doing some descriptive analyses before you're running bivariate models. So I want to talk through those as well. So when I talk about investigating your change model, we're talking about identifying a suitable growth curve. If you have 3 measurements per person, if that's your maximum number of measurements, you can only model a linear growth curve. Why is that? Because let's say you only have 2 points, you can't actually model anything. You know that the best fitting line between 2 points is just taking a ruler and connecting them. So there is no estimation, there's no variance around this. It would just be actually reporting the actual change over time as an absolute. So there's no modeling. But with 3, it would be linear. With 4, you can do a quadratic modeling. And this is how this goes up. There are, I had a student once, I think I mentioned him, he came from the business school and he had data about beer sales over 50 weeks of the year. So he had 52 time points and he was modeling a sinus curve and he had these from, different places. So it depends on how much data you have, given that we have more and more data points from apps and other things. Those model choices will become more and more important in the near future. But if we're talking about repeated survey measures, many times we have 3. Sometimes we get 4, and we're already getting really excited about that. So let's go back to this. 3 measurements per person, that's what we're starting with. So the question is, we can only model linear, but is this a good choice? Because if it's not, then we're having a problem. So what we're looking for is what are the patterns? And you would look at the plots of time versus your outcome variable for a selected set of participants. And you would look at individual OLS trajectories. So this is a line of best fit for each person that actually the software will do for you. Throughout this lecture here, I will be using SAS code, and the code is on Canvas, as is the SAS dataset. But as I've pointed out, there is the website that has all the code parallel for SAS data R and other software packages at the UCLA website. Now, what you will see across these graphs that each software package has not quite necessarily, but has some differences in capabilities and different ways of presenting the data. So when you go to the UCLA website and you go like, I'm not getting exactly what I'm getting on SAS, that's because the software package you're working with has different functionality. But let's go back to this. So we're trying to figure out what do the data actually look like. And this is quite informative. So I'll walk you through this. So here's the SAS code for what I will be showing you on the next slide and what you've seen in the second chapter of Singer and Willett. The SAS code is, you can look at it and you can try to fiddle with it, and I've fiddled with it to some degree when it comes to colors and thickness and other things. But in SAS, as in other packages, the graphical representation and the graphs and plots codes are not intuitive. So you want to go and really find a good example that gets as closest to what you want, or find somebody who can help you. But my experience is that we all kind of are limited to what we've been exposed to. So use all this from Singer and Willett and the UCLA website to your advantage. So here's the output, and these are 4 IDs that you see the actual data point. And I put a note in there. So if you're doing this with your actual data, these are publicly available data and they're de-identified. So we're talking about something that we can easily do. But if these are data that are protected, you have to be careful because these are raw data. These are actual data points that you should not be sending around through email. Within Emory, you're in an encrypted environment, but even there, I wouldn't do this. It's very easy for somebody to forward something to somebody who's not within the system, and you cannot email data. That being said, let's take a look. So what we see is that we see kind of some curving thing, but they go in opposite directions. And at least for ID 23, 32, and 65, I would say that a linear approach seems quite feasible. So this is just a slide that has the text to what I already talked through so that you also have it in writing. One thing that Singer and Willett recommend for looking at level 2 predictors, and this you could actually do for longitudinal data as much as you could do it for cross-sectional data, is to examine OLS fitted trajectories separate by levels. And so this works well for dichotomous predictors, or if you have a continuous predictor such as the pure alcohol use, you would choose a low and a high value to look at some contrasts. Here is the code for this, and if you know SAS, you see that there's some sorting by ID, so you have measurements sorted within ID, then there's a regression model, then you're merging some of this output, there's a correlation that you're looking at, and then there is some plotting in there. But again, as I said earlier, you want to find good code that you can adapt with minimal effort. So here's what you're getting for child of an alcoholic. On the left side, you have the trajectories of all the participants who are not the child of an alcoholic. And then on the right side, you have those who actually have an alcoholic parent. And you can already see that those patterns are quite different. Now, I think this is all you will get from SPSS and Stata, but SAS actually gives us another option that allows us to draw even stronger conclusions. Similar to earlier, here is just the text of what I just talked through, but we'll move into looking at the better output. I don't have the code here, but it's available online. So here you see the output from the better SAS code, and now the thickness of a line indicates is correlated to the number of participants that would fit into that trajectory. And now you see one big thing, you have non-alcohol users in the non-alcoholic condition, parent condition, many of them, and you have very few of this in this group, so it's like a zero group through time. And then we still see the pattern of the change over time, that we see that there seems to be a much smaller baseline range. When we look at the left graph, we see that there is nobody with scoring more than a 2 at baseline, while the full range is used with the other group. And then in terms of trajectories, we see quite some trajectories, and there seems to be also more declining trajectories in the right-hand side group, but they also start at higher points. So all these things need to be looked at together. And so what I would conclude from this is that COA is a good level 2 predictor because there seems to be some differences in baseline and some differences in change over time. So this would be a good predictor to model both the intercept, which is the baseline, and the time part of the model, which is the slope or change over time. So I've talked through most of this with the previous slide where we could see the diagram, but also I want to mention that you could have come to the same conclusion from theory. Sometimes, though, it's really nice to show things graphically, especially to a research team, because it's quite illustrative. These are descriptive data before you're actually trying to get some general estimates. And it shows you variation. It shows you if you're modeling certain things in a certain way, how much are you simplifying what you're actually proposing compared to what you're seeing in the diagrams. And they're just, I find them interesting to see. So I'm not going to go through the models and the output. All of that is in the chapter that chapter 3 of the book, but it's also in the models are in your handout. And this is not the purpose for this, but you will be building your models in sequences, and we've talked through that already last week. So I want to focus now on what to do after you run your models if you're doing growth curve analyses. So after you run the models, there are two tasks, and I actually we will talk first about examine normality assumptions for the level 1 and level 2 residuals. And that's kind of a strong repeat from what I've been talking you through for the cross-sectional models. And then presenting prototypical trajectories, which is somewhat similar to when we were presenting prototypical trajectories of interaction terms. So we already looked at this at HLM7. I'm going to use SAS for this right now, but HLM7 will do the same thing for you, and you can do it just the way we did it before. It can give you the level 1 and level 2 residuals, and if you have 3 levels, we'll give you for residuals for all 3 levels. The assumption again is that their distributions are normal. And so you want to do normal probability plots of the residuals. Now I want to talk about Singer and Willett recommending examining those for all presented models. I would argue this encourages you to not present too many models, but I would also say that you can discuss this for the final model and not present graphical evidence, which I really haven't seen in publications. However, if this is part of your dissertation, that's a different story because you have more space and it would be meaningful to walk people who review your work through this. So for the example that Singer and Willett present, here is the level 1 residual plot. And as you can see, that's pretty neat. There's very few outliers at the ends, and it looks very, very linear. So we're good here. For level 2, we're getting 2 residuals, one for the intercept and one for the slope. And as you can see with both here, they look pretty good. The one for the slope has a little bit more variation in it. And as we've seen already with the very individual plots, you know, a linear assumption is okay. But if we could have a quadratic relationship, it seems that the data would fit the model would fit better to the data. So that's what we're seeing here. But these are way good enough. So presenting prototypical trajectories, this is not necessary, but I think it is good for you to understand your data. It's way easier to talk about this if you have some graphical representation. And knowing that HLM and growth modeling is not that intuitive for a lot of people, this helps you communicate your findings in a more sophisticated, but B, also a way that more people can understand. So what do you do? How do you do this? You choose some meaningful predictive values, just the way we've done it when we looked at interaction terms. So it's similar in this. And then you plot the trajectories. And there are different ways. I'm going to walk you through the SAS code, but you could also just calculate and determine your prediction equations and then use Excel and graph this. Let me know if this is not clear on how this would be done with an equation in Excel, and then I can either refer you to classmates who know this. There's a couple of videos on YouTube. They're not the greatest, but I'm happy to create one and create a little video on this. So what we're doing right now, we're going to look at models B, C, and E. So there's going to be the unconditional growth model. The unconditional means model really doesn't tell you too much in a graphical representation. Then we're going to have COA as an uncontrolled predictor in there, and then we have COA as a controlled predictor where we're also having peer in the model. So here's the SAS code, and what you do is you actually run the model, and then you see you have an out statement in here. It's the out PM equals MB, which means that the prediction model parameters will be in an output file that's called MB, and that data file is the one that is used to plot the relationship that you have in there. So we're plotting the predictor, and that's from the output, any predictor that's in there, and then we're plotting age from the data there as well. And given that this is an unconditional growth model, there will only be one trajectory. This is the overall, the mean change over time across the entire sample. This is a mean baseline point. Where are we starting? At about 0.7 maybe. And then there's a change over time that gets us to a little bit over 1 on the outcome of alcohol use. So that doesn't tell us too much, but it tells us a little bit. I'm not going to talk much about this. Take a look at it, and then I'm going to talk about the graphical output. So here is the output from this elaborate SAS code, and I'm already at the point where I would like to take this into Excel or at least annotate it because I don't like the legend that is there. But what we have is COA is the grouping variable. So we have two lines here, and as you can see, I cannot distinguish which one is 0, which is 1. We know from the exploratory data that the lower one is the 0 group, so those who don't have a parent that has an alcohol problem are lower on baseline. But it seems actually that they're a little bit higher on change over time, which we also discussed because they have actually more room to change their behavior than those who already have been using alcohol at baseline more. Finally, here's the code for the last output. And as earlier, I won't talk through this, but it is here. So I rather want to talk about this output, and now this is actually, I think this is from a newer SAS version. So the book originally, Sing and Will It, was published in 2003. So at that point we were, I believe, at SAS 9.2 or even 9.1. And the graphical representations have gotten much better, as have like tables and things like this. So this is a newer presentation here. I would also adjust the code that it wouldn't show 13 and 17 in there. But now at least I can cleanly distinguish those kind of the trajectories. And what we have now are 4 trajectories. I could argue that I should color code this, but and it might make sense for class. But I also want to point out that you pay for color graphs in your papers, so most cases you will figure out a way to do it with these kind of patterns and then some gray shading to avoid having to pay sometimes hundreds of dollars for a color figure in your paper, even if you're not paying for regular publication. So just to put this on your radar. So you want to save those kind of things when you have real important things that you want to show and have to show with color, such as maps and more complex findings. So having said this, we now have COA, which is labeled as C here, at 0, 1, and 0, 1. We have a high peer drinking and low peer drinking. So it's the HP is high peer and low peer. So the lowest trajectory here is low peer drinking and not having a parent with an alcohol problem. And that's the lowest starting point. And it's also the lowest end point, but it is the steepest change. So this would be something where we would suggest we need to follow these adolescents longer to see if that continues or if things balance out over time. So what happens with this delayed onset of alcohol use? Then the second graph we have is the high peer drinking and not having a parent with an alcohol problem. And what you see here is that there seems to be more early experimentation going on. So there's a higher baseline value, but it's also the lowest trajectory. So there's the least increase over time in alcohol use in that group. So there's a dampening effect of the parental influence here and or genetics. So it's complicated with alcohol. Then the third highest trajectory here is high peer use and having a parent with an alcohol problem. And those last two are kind of interesting, I think. No, it's actually the low one and then it's the high one. So it makes sense. So if we're looking really that you have two negative influences that add to each other, but we also have to look at the change over time and where do they start and where do they end. So I find this, if these are really the two key predictors in your model, I find this graphical representation one that will allow you to show and talk intelligently about what your model has found. And so that's it. It's the end, and I'll see you in class.